Hello. In this last video, Limits Part 5, we're going to look at one final technique for evaluating some particularly tricky limits. Now, to start with, I want to have a bit of an analogy here. And for the analogy, we're going to imagine three people. We're going to imagine Bob, Fred, and Jack. And I want to figure out some information about their ages. In particular, we're going to assume that Bob is the youngest of all three, Fred is in the middle, and Jack is the oldest. Now let's say I know that Bob is maybe 32 years old, and Jack is 45. How old is Fred? Well, there's a lot of different guesses you might come up with. Maybe you think Fred is maybe 35. Maybe he's 40. Certainly he's not going to be 50 because Jack is only 45 and Fred's got to be in the middle. Certainly he's not going to be 30 because Bob's the youngest. But any age between 32 and 45 would be good for Fred. Now, that's helpful because it narrows down Fred's ages, but it doesn't give us Fred's exact age. Now, let's say instead, though, that Bob was 30 and Jack was also 30. How old is Fred? In this case, is there any doubt? Is there any uncertainty? Or do you know how old Fred is? Well, hopefully your logical brain is telling you that Fred is indeed 30 years old. Exactly. There's no question about Fred's age. He must be 30. Because if Bob is 30 and Jack is 30, then Fred, being in the middle, must be 30. And the interesting thing is you can determine Fred's age without asking him. You don't have to say, hey, Fred, how old are you? As soon as you know how old Bob and Jack are, you automatically know how old Fred is. Now, this logical process can be extended to work with limits. So the theorem is called the squeeze theorem. Now, a theorem means like a rule or a process, and we're not going to prove the squeeze theorem. It's, again, a little technical. We're going to assume it's true, but hopefully the analogy gives you the basic idea of it. And I'll go through the statement and then an illustration. So we need to first suppose that we have three functions, g of x, f of x, and h of x. And we need to suppose that those three functions are set up in an inequality so that g of x is the smallest, h of x is the largest, and f of x is in the middle. And this needs to be true on some open interval containing a, except possibly at a itself. Now, if we can show that the limit of g of x is L, the smaller one, and if we can show that the limit of h of x is L, the bigger one, then automatically the limit of f of x will equal L without us even trying. It just comes to us automatically. It's the theorem, the squeeze theorem. Now, let's look at an illustration. Let's say we have the following graphs. Here you have a parabola, and then you have another parabola, and inside you have this crazy green thing. Let's go ahead and label each one of these. So let's look at that very bottom one. Let's call that smallest parabola g of x. Let's call that big parabola h of x. And let's call that green thing stuck in the middle f of x. Now, would you agree that g of x is the smallest, h of x is the biggest, and f of x is in the middle? Well, let's look at the interval. Over the whole interval, it seems like h of x is always above the green and the blue. It seems like on the whole interval, the blue one is always below the green and the red. I think this is true. So we could put inequalities here. G of x is less than or equal to f of x, which is less than or equal to h of x. Comparing back to our analogy, this is our Bob function. This here is Fred, and over here is Jack. Now, if you look, what would happen to, let's say, Bob, to g of x, as x approaches 0? What does it look like we get for a limit value? Well, I think it's pretty clear. The limit as x approaches 0 of g of x is going to equal 0. Either side, you go from the left or the right, it doesn't matter. As you approach 0, you're going to get a y value of 0. And as you do the limit as x approaches 0 of h of x, you're also going to get 0. If you look at that parabola on the top, as you go to 0, you get 0. Which must mean, therefore, by the squeeze theorem, and you should say why it's true. So by the squeeze theorem, the limit as x approaches 0 of f of x must also be 0, because it's being squeezed between those two other limits. Here's again a Desmos if you want. You can take a look at this on a graph. Now, let's go ahead and try an algebraic example. So here we have the following limit, and we're going to go ahead and see if we can use the squeeze theorem without a picture but with some algebra. So we have the limit x approaching 0 of x squared times sine of 1 over x. Now if we plug this in, well, we're going to get 1 over 0, so right away that tells us, well, this is maybe like a positive or negative infinity, but then you're doing sine of that, and that's something we've never really dealt with. So plugging it in doesn't seem like it's going to get us anywhere. What I want to do is I want to set up an inequality like I had before, but I don't have anything to work with. And so what I'm going to start with is just the basic portion. There's a sine, and I know something about sine. I know that sine of theta has an inequality. Sine of theta is always between -1 and 1. If you think of your classic sine graph, the biggest it goes is 1 and the smallest it goes is -1. Now, that might be true for sine theta, and so it's also true for sine of 1 over x. Anything inside the sine function will still be bounded between -1 and 1. Now, what I'm doing here, just so you're aware, is this right here, this is my target function. Target function. I want to somehow make this function. And to do that, I have to find some way to build it. I have to create it. I have to get that target function inside of an inequality. And the first step here was showing that sine of 1 over x is between -1 and 1. But I'm missing something. This doesn't quite look like my target function. I'm missing an x squared. Let's go ahead and multiply the whole thing by x squared. That's something you're allowed to do in math. You multiply everything. So I'm going to get negative x squared less than or equal to x squared sine 1 over x less than or equal to x squared. Now this is important. I'm allowed to multiply and it doesn't flip the inequality because x squared is always a positive number. Well, positive or 0. And so because it's a positive or 0 number, it's not going to flip my inequality. It's not negative. So I'm good to go there. Now, let's look. We have inside our target function, and on the outside we have two other functions. What happens to those functions as x approaches 0? Well, the limit as x approaches 0 of negative x squared is going to be 0. And the limit x approaches 0 of x squared is also going to be equal to 0. Okay, therefore, by the squeeze theorem, the limit as x approaches 0 of x squared sine 1 over x is equal to 0. And so we've shown, like the example requested, that this limit equals 0. What's actually interesting to note here is this algebra that we just showed is the exact same as the graph we had above. And I'll show you that on Desmos. So here you can see my parabola on top was actually x squared. The parabola on the bottom was negative x squared. And the crazy function in the middle was indeed x squared sine of 1 over x. So that crazy function, although you can't plug in 0 to it because you get a 1 over 0 and then you have an infinity and then you have a sine of infinity and none of that makes any sense, when you use the squeeze theorem, you realize that the top parabola squeezes it down to 0 and the bottom parabola also squeezes it to 0, which means that this thing can't escape and the limit as x approaches 0 must be equal to 0. Now let's try another one where we don't know the answer. So in this case, we're going to evaluate the limit as x approaches 0 from the right of root x times 1 minus sine squared 2 pi over x. Again, this is going to be a squeeze theorem problem because there's an x on the bottom here. So you're plugging in 0, that's going to give you a type of infinity. That doesn't make any sense to take sine of infinity. So we have to do some type of squeeze theorem. And in particular, if you notice, there's a 1 minus sine squared. So I'm going to keep in mind the important identity. Hopefully you remember, and we'll be reviewing these in a future video. Sine squared theta plus cos squared theta is equal to 1. So in other words, I'm going to rewrite this as 1 minus sine squared theta is equal to cos squared theta. So I'm going to build my identity, or my inequality, I should say, around cos of theta. So cos of theta, that's between, again, -1 and 1. Now I don't need cos theta, though. I need cos squared. What's cos squared between? What are the values that are the biggest and smallest for cos squared? Well, certainly the highest value would be 1, because 1 squared is 1 and you can't get any bigger than 1. But what's the smallest value? Well, you might think to square this and also put 1, but that would mean that cos squared would always be equal to 1. I don't think cos squared is always 1. That doesn't seem to make any sense. Let's pull up a graph here and see if we can understand what's going on. So here we have our graph of cos x, and we can imagine trying to square this graph. Well, when you square something, all the negative values become positive. And so cos squared looks kind of like this. The top value, 1, gets squared to become 1. But the bottom value of -1 gets squared to become also positive 1. And what happens is all of these negative values down here kind of flip up to become positive. So cos squared actually has a smallest value of 0, because 0 squared is still 0, and then a top value of 1. So when we go to make our inequality, it looks like this. Cos squared is going to be between 0 and 1. Now I can go ahead and convert this into a 1 minus sine squared. So I have 1 minus sine squared theta. And I can convert that theta into a 2 pi over x because it's true for any theta, so it'll be true for 2 pi over x. Again, right now I'm trying to make this inside look like this. This is my target function. And it doesn't look quite like my target yet. I'm missing a root x. Well, I can multiply everything by root x because the square root of x is always positive. So I'm going to get 0 times root x, which is just 0. Root x, 1 minus sine squared, 2 pi over x, and then root x. Well, let's go ahead and try the limits now. We've got our target function in the middle. So the limit is x approaches 0 from the right of 0. That's the left part. It's just going to be 0. The limit of a constant is a constant. Limit x approaches 0 from the right of root x. That's just going to be root 0, which is also 0. So therefore, by the squeeze theorem, the limit as x approaches 0 from the right of root x, 1 minus sine squared 2 pi over x is equal to 0. Now let's go ahead and think about a situation where the squeeze theorem doesn't apply. So why doesn't the squeeze theorem apply to the following situation? Limit x approaches 0 of fx, where fx is the red function. So go ahead and think about it, either A, B, C, or D. All right, so hopefully you've thought about it. The answer would be D. The squeeze theorem doesn't apply because the upper and lower function don't have the same limit. As x approaches 0, the blue function is going to give me about maybe 1.5, 1.5, and the green function is going to give me 0.5. But those two values aren't the same, so we can't say anything about the limit of fx. And in fact, we probably wouldn't need the squeeze theorem for this function. I think we could find the limit of this as just equal to, well, it looks like it's equal to 1. We probably wouldn't need the squeeze theorem in this case. And so you need to be careful when you do and don't apply the squeeze theorem. In particular, you need to make sure that you have the same limit for the upper and lower function. Now for homework, you can go ahead and try the questions on page 103, 35 to 46, and limit worksheet part F. And as always, thanks for watching.